Hello, my name is Dan Brunner, and in this video, I'll be going over how to solve problem 2.21 from Chapter 2 in the Fundamentals of Mass and Heat Transfer textbook. So looking at the problem statement, we're told that we have uniform internal heat generation occurring at 5 times 10 to the 7th watts per cubic meter. This is occurring in a cylindrical nuclear reactor fuel rod with a diameter of 0.06 meters. For part A, we have steady state conditions, and we have a temperature profile given by A plus BR squared, where R is the distance from the center line of the cylinder in the radial direction. We also have these constants A and B, and then we're given the fuel rod properties, including the thermal conductivity, the density, and the specific heat. So for part A, we're trying to find the rate of heat transfer per unit length of the rod at the center line and at the surface. And then for part B, we're going to increase the power level of the reactor suddenly to 10 to the 8th watts per cubic meter. And we're going to find the initial time rate of change, time rate of temperature change at both the center line and the surface. So here's what we're given. Um, and we're trying to find again the heat transfer rate per unit length at the center line and surface for part A, and then the time rate of change of the temperature um, after the heat generation is increased. So what assumptions can we make to help us solve this problem? Well, first, we're going to assume that we're under steady state conditions. None of the variables are time varying, including the temperature. And so any time derivatives go to zero automatically. For part B, we'll be dealing with the transient system, however. So this assumption is only valid for part A. We're going to assume that each cylindrical layer within the fuel rod is isothermal and has the same temperature all throughout that layer. We're going to assume that we have constant isotropic properties, meaning that the thermal conductivity in the radial, well, in all directions, is just equal to K. And then we can bring that term out in front of all of the derivatives um, because it is not varying with respect to that, well, in that direction. We're also going to neglect convection and radiation at the rod surface. We're only going to be considering the conduction within the rod. And then that conduction is going to be acting radially, so there will be no heat transfer in the z direction. So for part A, the governing equation that we'll use is Fourier's law per unit length. So we have to divide by that L term. For part B, we'll be using the heat diffusion equation, and that'll be the cylindrical coordinate form. And we also have this temperature profile equation that is a quadratic equation. We'll be dealing with some radial derivatives of that equation. So for part A, I went through and simplified the Fourier's law equation per unit length. So we're neglecting the phi and z derivatives. And so we're just left with negative K times the cross-sectional area that the heat transfer is occurring through, divided by the length of that section of the fuel rod. And then we're multiplying all of that by the dt dr derivative. And that derivative, if we differentiate our temperature profile, just equates to 2br. And so plugging that back into Fourier's law, we get our heat transfer rate per unit length to be equal to -4 times pi times the thermal conductivity K times that constant B times R squared. So if we plug 0 in for R, we get 0 watts per meter at the center line for the heat transfer rate per unit length. And then if we plug in 0.03 meters for R, which represents the distance at the surface of the rod, we get that the heat transfer per unit length is equal to 1.79 times 10 to the fifth watts per meter. Looking at part B, we're going to be simplifying the heat diffusion equation in cylindrical coordinates. So we can get rid of the phi and z terms in the equation because we're only considering conduction occurring in the radial direction. So we have that radial direction term plus the heat generation, and all of that is equal to the density of the fuel rod times the specific heat times the time derivative of the temperature. And that's what we're trying to solve for in this part. And so if I go through and again substitute in the derivative of the temperature profile with respect to R, we get that the time derivative of the temperature is equal to 4 times K times B plus Q dot 2. That is the increased heat generation rate that we were given, all divided by the density of the fuel rod times the specific heat. And so plugging all the numbers in, we get 41.9 Kelvin per second for our time rate of change of the temperature. And so that is how to solve problem 2.21. Thank you.